something called this whole chapter is about differential equations. Okay, we've somewhat been exposed to differential equations already. Okay, what do I mean by that? You've had problems that look like this. F prime of x equals x plus 1. What would f of x be? Okay. We know that because we can just take the integral and get to the next one. Okay. What we are going to work on today is what we call separable differential equations. Okay. So we're going to get something like dy dx equals this. Okay. Well, I guess. If we have a derivative in terms of x and y, but maybe it's written as a fraction, maybe it's written as a product, we can separate our variables. X is on one side, y is on the other side, and integrate both sides from there. So what we're going to look at today are differential equations that have both variables. And the process that we're going to do is what we call separation of variables. It's exactly what it sounds like. We are going to separate our variables. So this is what's going to happen. I'm going to give you dy dx equals something. Okay? You need y and dy on one side. You need x and dx on the other side. Those of you who like steps, here you go. Okay. Whatever the function is in terms of y, get it with the dy. Whatever the function is in terms of x, get it over with the dx. Okay? Then what's going to happen is we're going to integrate both sides. So you're going to have an integral with dy, and you're going to have an integral with dx. And as long as we do the same thing to the right side as the left side, we're safe in terms of following the rules of an equation. Okay? We're balancing it out. Okay? It's not going to be pretty right away. More than likely, I mean, very rare cases are you going to get y equals something. All right, so I'm going to ask that you go ahead and solve for y, reduce anything that needs reducing, clean it up, make it look pretty. We're going to do some examples. We're going to do 2 examples of these so you can see how they go. If you recall back in Unit 4, I also asked you to do something called find the particular solutions. Can anybody off the top of their head remember what that meant about an integral? Okay, we have, yes, and ultimately we figure out what C is, okay? So if I ask you for a particular solution, we're going to do the same thing. We're going to integrate by separation of variables, but then we're going to actually solve for C and rewrite it as a particular solution. So instead of y equals x squared plus c, maybe we would be writing y equals x squared plus 5, or whatever it is. We're basically solving for c and rewriting it. So we'll do two examples for each of these types of problems. Even though I'm teaching you a new technique, we're still doing our same integration from Unit 4. just got to brush up a little bit. We're not doing Flannel Fridays anymore for STEM.
So on Saturday.
Oh, it is Thursday. Dang it.
Thanks for the reminder.
Yeah. Does it feel like a Friday to anybody else?
Yes.
Like, I'm not the only crazy one? Okay.
I only know it's Thursday because we had NHS this morning.
Yeah, I know. I was there. Yeah.
Are you doing okay?
Yeah, yes. Go ahead and write this example down. Gosh, that's embarrassing. I'm wearing jeans today. That's also throwing me off. Usually don't wear jeans on a Thursday. It's usually just a Friday thing. Okay, so we have dy dx equals 3x squared over y squared. I want the y's with the dy and the x's with the dx. What could we do? We could cross multiply, right? We could multiply over the y squared. To be with the dy, we can multiply the dx over with the 3x squared. Now, we're going to integrate both sides. Okay. Antiderivative for y squared. Okay. And antiderivative for 3x squared. Okay. Now, don't be annoyed with me here, but first of all, are these c's the same? They're both plus a constant, but we don't really know what they are. But are we probably going to combine them together to be a constant? Okay, I can subtract this over and we still have a constant. So it's okay. Since we know we have plus c on both sides, let's just keep it simple and only write it on the right side. Okay, just to save us a step in our algebra. Okay, we know it's there, but we're just going to combine them together and still call it plus c. We're not going to call it anything different. Okay? I would like you to solve for y when you write your general solution. So, I would expect you to multiply both sides by 3. What's 3 times a constant?
3c.
But it's still a constant. Okay? Especially if we're not going to find c. We can just 3 times c is still a constant. I don't want it to be crowded in my answer. Okay? And then to solve for y, we would want to cubed root both sides. So y equals the cubed root of 3x cubed plus c. There is our general solution to the differential equation. Now, that's a pretty basic example, okay, and that will probably mirror your first few problems in your homework, okay? Well, where we need to be careful is when we end up getting like a natural log in our antiderivative, okay, or as our antiderivative. So let's look at an example where we might need to be a little bit careful there. So go ahead and write this one down. parents all got emails about the plumbing issue, so they're all aware of what's going on. But stick to this side of the building to go to the bathroom and wash your hands. I think it's more about like, did you wash your hands? Okay, last time we cross multiplied. That's not going to be helpful in this case, right? We need x with dx and y with dy. So if I want y with dy, we're going to have to divide over the y. And if we want x with dx, we're going to multiply the dx to the other side. So I'm writing it like this so that I can see a little bit easier what my antiderivatives are going to be. But, you know, you could write it dy, we divided the y over. But I think it's easier to see what our antiderivative is if I write it as dy off to the side. Do you see what I mean by that? Like, is that okay, me writing it? Our plumbing has been fixed. Look at that. Restrooms all open. There you go. All right, so now we're going to integrate both sides. The antiderivative of 1 over y. Okay, but you're right,
It's
plus
on the
c,
other side.
but we'll keep it on the right side with the other one. The antiderivative of 1 over 1 plus x. Yeah, it is. The natural log of 1 plus x. Now we need to solve for y. What function helps us solve for a variable inside of a logarithm? E. E is our helper in this case. So if I take both sides as a power to e, well, these cancel. Okay. These don't cancel quite yet because of this plus c. Okay. Now let's flash back to Algebra 1 for a moment. Properties of exponents. If we are adding our exponents, when we break it apart to like base to a power, right? So thinking like frontwards, I'm kind of trying to get you to think backwards, but thinking frontwards, if you have x squared times x cubed, we get to add our exponents together. Okay, so we can break this apart to be e to the natural log of 1 plus x times e to the c. Okay. All right, well, at this point, boom, those are going to cancel. And what's e to the c?
C.
It's still a constant, isn't it? E is a number. So we have 1 plus x times some constant. We've solved for y. We've reduced anything that we've needed to reduce. Here is our general solution to the differential equation. Interesting, you say? But do you see what I mean? We're not really doing anything obnoxiously new. Just kind of a different approach to some knowledge we already have. Okay. All right, well, let's go ahead and look at some examples where I actually give you a initial condition. That's the word I'm looking for. So here I have a differential equation and an initial condition. No, we'll kind of talk about that. All right, so Brindley asked a good question. Which one does the negative go with? It cannot go with both, otherwise it would be a positive fraction. So you have to pick one. But thinking ahead of the game, if you know that you're going to have to solve for y, I would try to keep the least amount of coefficients, if possible, with y. All right, so when we cross multiply, in this case, that's going to work, right? Y dy, I would leave the negative with the x, dx. So we can integrate both sides.
They closed worlds for WGI and they canceled the rest of Flanders.
Happy note. What's the antiderivative of y? 1/2 y squared. And then the antiderivative for negative x, negative 1/2 x squared, and then we'll put the c plus c just on the right side. You did have to get a little bit closer. You don't have quite the range. All right, now, y squared is going to be, when we multiply the 2 over, negative x squared plus 2 times a constant, still a constant, this is where I need you to be careful. When we square root both sides of an equation, what do we have to include? Plus or minus. This right here, this is our general solution. This is where we would have stopped in our previous 2 examples. But I have given you an initial condition. Our initial condition is y of 4 equals 3. So when x is 4, y is 3. Okay. So what we're going to do, first of all, how do I know if I should use the plus radical or the minus radical? Y plus. Well played, Alex. Easy. We have a positive y value, so we need to pick the positive y value. If this were a negative y, we would be picking the negative radical, so that would match. So, since it's positive, we can pick the positive. So, was it 4 for the y? And 3 for the x? Because that's a negative x squared.
Oh, it's outside.
Mm-hmm. That's why I asked. You guys agree? 3 like that. I hit it, so I can't remember. All right. What do we get for C? 25. So our particular solution Obviously, my mind is confused. I'm not about to try to spell particular in front of all of you up here at the board. Y equals positive radical negative x squared plus 25. You can write particular. I know it's not going to go well. I tried to spell it. I think it's Friday. For Friday. Not pertinent to the process, but what is that equation resembling?
Circle.
Full circle? Semicircle, top half, right? Centered at 0, 0, radius 5, okay? Right here, this is a full circle, right? Positive for the top half, negative for the bottom half, okay? And then we get a particular solution for just the top of the semicircle, okay? All right, one more example. Go ahead and write this down, and I'm going to give you the opportunity to only do the work to get the general solution. Do not plug in 1 and 3 yet. I want to do that part together. But at your table, with the assistance of your peers, I would like you to do the separation of variables to get to only the general solution. 1, 2, 3, go. It is okay to talk to each other. Very good.
Oh, okay. I was like,
I disagree with that. Only 1 over x is x over x. But 1 over x squared is the same thing as x to the negative second, and you could use a cardinal. The antiderivative for 1 over x squared is not a natural log. It is a power rule problem.
so in my integral, I can change it to
X to the negative 2. It'll be x. It'll be negative x. You have that much, right? Becomes your power to e on both sides. So you should have y equals c e to the negative 1 over x. Or if you left it as negative x to the negative first, that means the same thing. There's a step that I showed in a previous example that I skipped in this example. Do you want me to put it back in so you can see where the c, how the c became coefficient?
Okay, what's the
Like the step that I didn't show.
no, like
E to the negative x to the negative 1. Like I wrote it as 1 over x. Maybe you wrote it as x to the negative first.
would
You
you have
have to have the c out here, yes.
no, do it as you do the other side.
Yes. Because if you do something to the left side, you have to do it to the right side to keep it balanced. Okay. So 1, 3 is our initial condition. So C would be 3 divided by e to the negative first, which really is the same as what? If I'm dividing by e to the negative first, it's just 3 e to the first, because we can just bring that up. So the reason I wanted to do this together, A, for that purpose, B, I would be okay if you wrote 3e times e to the negative 1 over x power. But if this were like a multiple choice question, this would not be one of their answers, okay? This is e to the first power, right? So it makes sense that if you have 2 of the same base multiplied together, that we go ahead and squish them together. So we would write this as 3e to the 1 minus 1 over x, because we would add those exponents together. I'm actually going to write one of your homework problems up on the board. Number 1, I'd like you to get a head start. Number 2, there's some notation that I want to be able to talk about. Okay. Your homework is 1 through 17 odd. I am not going to write down number 1. So if it bothers you to go out of order, maybe skip some space. I'm going to write down number 7. Number 7 is 2 plus x y prime equals 3y. Okay. Every single example I did up here had dy dx. Where the heck is the dy dx, Miss Bowen?
It's the one.
Ah, it's just y prime. Okay, you're going to get some problems that have the y prime. Just rewrite the y prime to be dy dx so you can do the separation of variables. So before you walk out the door, I want you to do the separation of variables to find the general solution to that guy right there, number 7. Okay? When you have your answer, let me know. I want to check it.